In the next set of slides, we'll go through many special cases and different ways of interpreting matrix multiplication. And just like the properties from the last video, all these different interpretations and special cases will of course follow immediately from that one definition of matrix multiplication we gave in the first slide. But they are different important cases or different important ways of interpreting matrix multiplication. And so because of this, it's good to develop a strong intuition about the different things that matrix multiplication can be doing. Let's start off with vector-vector products. Vectors are special cases of matrices that have only one column and some number, say n rows. And here, x and y are both going to be vectors that are importantly the same size. So one very important special case of matrix multiplication is what's called an inner product of vectors. This is written as x transpose times y. Remember, x and y are both, in effect, n by 1 matrices. So we couldn't just write the product x times y here, right? That would not be a valid product. What we can do, however, is transpose x. And in that case, x transpose is now a 1 by n vector times an n by 1 vector. So what we get in the end will be a 1 by 1 vector, which is just, of course, a scalar value. So the inner product, x transpose times y, is just going to be a single scalar value. And by the definition of matrix multiplication, what this will actually be equal to is the sum of the product of all corresponding elements xi times yi. So we take our vector x transpose, which equals, should I write it like this? X transpose is a vector like this, times our matrix Y. We take all the corresponding elements, multiply them together and add them up, and that is our inner product x times y. Another type of vector-vector product is the outer product between two vectors. So here, x is a vector in Rn, and y can be a vector in a different size. Y is in Rm. The product x times y transpose will be a matrix. This product of two vectors is actually a matrix in n by m. That's easy to see, again, just from the dimensions of these things, right? Because x here is going to be n by 1. Y is m by 1, so y transpose is 1 by m. And so the product of these two things is going to be n by m. And each element of this matrix is just a product of two elements in these vectors. And in particular, the ij element of x, y transpose is just going to be the ith element of x times the jth element of y. So unlike in the inner product, where we only multiply together corresponding elements of the vector, which required, of course, the vectors to be the same size then, in the outer product, we have all possible combinations xi and yj for I equals 1 to m, n, and j equals 1 to m. Now let's talk about a slightly more complex case where we're multiplying a vector by a matrix. For a matrix A in m by n and x in Rn, Ax is itself going to be a vector in Rm. Again, A is m by n, x is n by 1, and so their product is just a vector now in m by 1, or a vector in Rm. And there are a couple ways to interpret matrix vector products. We'll talk about two of these. In the first case, let's write A in terms of its rows. So the first row of A will be A1 transpose, etc., up to A sub m transpose. In this case, what the definition of matrix multiplication says is that A times x is itself a vector where each element here is the inner product of a row of A and the vector x. Right? So we take each row of A, we form the inner product of A and x. So first A1 transpose times x, that's the inner product of A1 and x. Then A2 transpose x for the second element, all the way down to AM transpose x. And this way, every different element of this vector here is an inner product of x and a row of A. Now that might be the most obvious interpretation because it follows pretty straightforwardly from the definition of matrix multiplication, how we defined it as being a set of inner products between the rows of A, and in this case it's only one column of x, so it's going to be a set of the rows, inner products of the rows of A and the column x. But we can also interpret it another way. So if we write A by its columns, so we're going to write A now as A1 being the first column of A, A2 the second column, etc., up to AN. In this definition, we can also write the product A times x as a vector in Rm. But here what it is it is actually a linear combination of the columns of A, so it's the sum from I equals 1 to n, of AI, the ith column of A, times xi. So what this is we're taking these rows, we're multiplying them by the corresponding element xi, and we're adding these all up. So we have here x1 times a1. Remember, a scalar, x1 here is a scalar, so a scalar times a vector would just be scaling every element in that vector by x. And we're doing this all the way to xn times an. This equals a times x. So of course, these two ways of writing the matrix vector product A times x are obviously equivalent. If you write out, they just both follow from the same definition of matrix multiplication, so they give, of course, the same answer for what A times x is. But it's important to think of this product in two different ways, either as a set of inner products between the rows of A and x, or as a linear combination of the columns of A, where the coefficients on that linear combination are the values in x. Finally, let's also look at a bunch of different ways of thinking about matrix-matrix products. So here, and in the following, A is going to be a matrix in M by N, B is going to be a matrix in N by P, and in fact, sometimes we'll just omit writing these because from how we write A times B, it should be obvious the dimensions they have to have in order for this to be a valid product. So let's write this in this product here, A times B, in several different ways. To start with, let's take kind of the first definition we saw when we first described matrix multiplication and first defined it. And let's write A in terms of its rows and B in terms of its columns. In this case, as we saw, the ij element of this product is going to be equal to the inner product, the vector inner product of the ith row of A and the jth column of B. So for example, A, B, 1, 1 would just equal A1 transpose times B1, the inner product of A1 and B1. We can also write this in different ways though. So let's now instead write A in terms of columns and B in terms of rows. That's the reverse of what we had in the previous slide. In this case, A times B can be interpreted as a sum from I equals 1 to n of all the possible outer products AI, BI transpose. So what we do is we iterate from I going from 1 to n. We take the first column of A, for example, and the first row of B, form the outer product. Those are both vectors of the same size, so we're going to form the outer product of those two vectors. And we're going to iterate this for I equals 1 to n and sum up all these outer products. These are, of course, all the same size. I want to take the sum of all these different matrices. That is also equal to the matrix product A times B. So we can view A times B as either a set of many different inner products or a sum of outer products. Finally, let's leave A as a complete matrix and write B by its columns. So we're going to think about the columns of B being different vectors. In this case, A times B equals a matrix where each column of that matrix, so the first column of this matrix, is equal to the first column of B times A, the matrix vector product A times B1. That is the first column of this matrix here. The second column is A times B2, etc., up to A times BP. Remember, there are P different columns in B. And of course, this matrix vector product we can interpret either as a set of inner products or as a linear combination of the columns of A. As I said before, of course all these things are equivalent, but it's important to understand these different definitions and these different interpretations rather, because oftentimes we'll want to define a matrix product to have certain properties, and it will be very natural to do so if we can interpret it in these different ways.